Okay, we continue to study Feynman rules. The previous class we studied the trend T matrix element is I times the four-dimensional interaction Lagrangian, and we have derived the Fermi's golden rule that if we make use of the normalization for the scalar wave function, then it was n to the fourth power, 2 pi to the fourth power, four-dimensional delta function, and invariant matrix element. If we square this value, we can substitute this result in here. N to the 8th power, 2 pi to the 4th power delta function is squared, and invariant matrix element is squared, which is gauge invariant and a Lorentz invariant. We just copied the same method that was used when we derived the Fermi's golden rule. If I have two delta functions, just keep a single delta function and pull out the other delta function with 2 pi with the same power as the number of delta functions. And if we rewrite this as an exponential integration over the integration, because P1 plus P2 equals 0, if I substitute 0, then this delta function is just infinity. But this infinity actually means that space and time. And there is three-dimensional space, which is volume of a box that contains a state, and time is the interaction time. So this shows that t squared, this is not time, this t matrix element squared is increasing as time goes on and increasing as the volume increases. So we have to renormalize this by this over factor. So if I divide this time and space of the state, then we can define some probability of this kind of transition. Suppose a particle is coming in always, then if there is some rate of interaction, then you will have many interactions. But if you stop firing some bullet, then it does not interact anymore. And if I have a wide enough target, it has more rate of making interactions. So this probability density is rather related to the density, relative density of the two particles they collide. Okay, so important thing we have to remember is that we have to renormalize it by the interaction time and space. And the final result for the transition probability per time and per unit time and per unit volume is like that. So that is proportional to the delta function that keeps energy and momentum and the square of the invariant amplitude. So invariant amplitude is in general this kind of form. Current interacts with another current, and when the current disappears, then it is connected by some propagator that is virtual particle. All right. If we recall this wave function for the simplest case, that is scalar particle, and we just have free normalization factor n, then why don't we integrate over this space? Then the exponential factor just cancels, and what we have is n squared normalization factor times the volume. That suppose a free particle is inside a box. All right. If this particle is just a single particle, then we can choose the normalization to be just 1 over square root of v. Okay. So if I substitute this result, then transition rate, transition probability it was proportional to the n to the 8th power. Now it becomes 1 over v to the 4th power. Okay. 2 comes from the initial state. This guy has two ends. This guy has two ends. There are 4 ends in the amplitude, and in the squared amplitude there appears 8. Now we would like to make use of this result to define the cross-section for the cross-section that is relative to the probability of making interaction between two particles that are colliding together. As a first step, we first define number of density per volume. As we have studied, the interaction is proportional to volume and space and volume. And if I have only a single particle that hit together, then the probability of making interaction is well defined. But if we have a state that is coming in continuously, okay, then the probability for a single particle collision, if there is a probability, then if we have many particles, for example, fix one particle as a single particle and increase the number of particles, target particles, then the probability of having interaction is proportional to the density of the state. And suppose if I throw the ball with some frequency, then if I increase the frequency, then interaction will increase. For example, if I throw a ball single time per day, then the probability is less than the case case that I throw the ball per unit hour, right? The rate will be increased by factor of 24, something like that. So I'd like to know, in a single case, if I know the probability for the single particle interaction, then I have to generalize it to the case when they flow continuously. Okay. So number density per volume is very important. Before we define cross-section, we need to know something about flux. You know, flux is number density times the velocity of an object, right? So number density, why don't we compute the number density making use of this wave function? If I have a wave function psi star psi, phi star phi, then we have made normalization to be 1 over square root of v, then this normalization is just 1 over v to make the number of state just 1. Then number density for the rest particle when the forward momentum is just 0, then it will be just 1 over v0, where v0 is the rest volume of a box in which particle is just at rest. If a particle is moving, the space is now contracted. Okay, space is now contracted, so this v is increased. V is decreased. Right, so the number density increases by a factor of gamma. Right? And the gamma is just energy of that particle divided by rest mass. Remember? P mu is E and P vector, and E equals M gamma, if I use a C, then N gamma C and M gamma V, right? You remember it is M times U mu. That is M gamma C gamma V, right? So if we remove C, then M gamma, that is the energy. So E becomes M gamma, and P becomes M gamma V, right? So E equals gamma equals energy over rest mass, right? If you use a full expression, energy over mc squared, right? And okay, momentum is energy over speed of light times v. C squared. So this is the rest case, this is moving case, and they are not symmetric. So we had better have a symmetric expression. It is natural to have a density 1 over V, but now I think it's better to introduce a new number density. So we redefine the number density to be square root 2e, because the reason why we use that factor is in the phase space we have factor of 2e. You remember, if you compute the propagator p squared minus m squared plus I epsilon e to the minus I p dot x d to the fourth power x. If you compute the x0 integral, you will encounter, it was I forgot, it is minus I, right, 2e of p 2 pi to the third power theta function x0 e to the minus I p dot x plus theta function minus x0 e to the I p dot x, right? We had this kind of over factor. It is a little bit uncomfortable if we keep having this. Finally, you will find that this guy will cancel if we introduce a new number density. That is a number density multiplied by square root of 2e. I mean, we redefine this one to be square root 2e over v, something like that. Okay? Okay? Then when you square this, it becomes 2e over v. Okay? So in the rest frame, energy becomes a mass, and this is a rest, right? And if it is moving, then what happens? This was invariant, and it is replaced by gamma V0. Volume has been changed, and then it becomes like that. Okay. one particle is moving with velocity VA, the other particle is moving in opposite direction with VB. And that is not a single particle, but it has some, even though it is a single particle, as you know, if you make use of quantum mechanics, you cannot say a particle is placed at a single point. It is just distributed all over the space, right? So we have to make use of the density of state, something like that. So flux is actually number density times velocity. But suppose the two particles are colliding together. So two beams are colliding together. Okay? In the space, there are particles with number density Na. All of them are moving with velocity Va. And there are family of particles, they are equally distributed, or uniformly distributed into this in this space with number density Nb, and that is moving in the opposite direction. In that case, relative velocity is proportional to the flux, and number density of each family of particles should be multiplied to have a flux. Okay? We just copy the result of the previous result, that Na is now redefined to be 2 times energy divided by volume. 2 times energy divided by volume of the space. Okay? So when we call this V, we are just standing, and we have the size of box. And EA and EB is the energy of a particle, energy of the other particle, and velocity. So just like what we have done previously, we would like to multiply this one inside the absolute value. If I multiply this inside, then it becomes EA times VA. EA times VA, if I put C equals 1, then that is a momentum of A. So it becomes momentum of A. But we also have a vector EB that should be multiplied together. So after multiplying both vectors inside, VB means EB to make a PB, a vector, and it becomes EA. You know, if they collide together, they should make a head-on collision. So we'd like to choose one direction, then the other one has a negative direction to make a collision. Sure, if something is much faster, then it can hit in backwards, but we usually consider the case when they make a head-on collision. In that case, this vector sum, in one-dimensional case, this vector sum can be rewritten as just a simple sum. Because this guy is a minus P is proportional to PA, right? Minus PB. PA and PB are in different directions. So I have removed the absolute value outside. And each of them are positive now, right? But I'd like to show you this guy is the same as this one. There are complicated results, but let me recalculate in here. PA EB plus PB EA. square. It is not easy to compute directly, but let me just square this. Then PA vector squared EB squared plus PB vector squared EA squared plus 2 times PA PB EA EB. Right? But PA and PB, the two vectors, PB and P minus B are parallel, right? PA and PB are anti-parallel. They are like PA is going to the right, for example, then PB is moving backward. We are just considering a one-dimensional case. So this guy is actually minus 2 times PA dot PB. Right? And this guy can be rewritten. Why don't we make use of energy? EB squared minus MA squared. EA squared minus MA. This is momentum squared. And EB squared plus EB squared minus MB squared EA squared with this. Okay? So we expand everything, then EA squared, EB squared, EB squared, EA squared. So we have 2 times EA squared, EB squared, and minus MA squared, EB squared, minus MB squared, EA squared, right? And then minus 2 times PA dot PB, EA, EB. So this is the left-hand side, this is expression A. Expression B is PA4 vector dot PB squared minus MA squared and B squared. This is EA PA dot EB PB squared minus MA squared and B squared. Scalar product EA EB minus PA dot PB squared minus MA squared and B squared. Okay? If you square this EA squared EB squared minus plus PA squared PB squared, and then minus minus MA squared MB squared, and crossing term is minus 2 EA EB PA dot PB. Okay? Fortunately, we have the same contribution. This guy, they are the same. What about this and this? Because we have replaced PA squared by EA squared minus MA squared, so what I have to do is replace this one. Okay? This one gives the same thing, 2 times EA squared, EB squared, and EA MB, MA EB, minus and MA squared, MB squared, they cancel. So, if I compare this one this one, they are the same. ma squared dv squared. This guy, they are the same. This one, same. And this one, they are the same. Therefore, if I erase everything, therefore, flux of two colliding particles with velocity va to the right VA, VB. If two particles are colliding together, then the number density of each particle is Na equals 2Ea over V, and Nb equals 2Eb over V, and relative velocity Va subtracted by Vb, these product is the flux of two colliding particles, then the flux is just 4 over V squared, the square root Pa dot Pb squared subtracted by Ma squared and B squared. Again, note that I have redefined the normalization for the number density to be proportional to the energy scale. Okay. So by making use of these results, we will define the cross-section and discuss the meaning of the cross-section in the next class. That's it.